Good morning, students. Today we'll see the potential due to the gravitational potential due to the spherical cell. For this, we'll consider a spherical cell of radius r and a point P is at distance r from the center of the spherical cell. Now, the point P is at distance r from the center of the spherical cell. Now, we will cut the slice, join this point P and O, join OP and cut a slice CEFD. Cut a slice CEFD as shown. Cut slice CEFD as shown. Here, this is C, this is E, and this is F. This is a slice of this spherical cell. This is also a small spherical cell. In this way, we can cut a number of spherical cells in this cell. And for calculating the gravitational potential, we have to calculate the potential at point P due to this cell, and lastly we have to integrate this potential for calculating the total potential due to this spherical cell. Now, we will consider geometry. Now, for that, we will consider the figure as shown in the figure. We will calculate suppose this point is K. Now, in triangle EOP, let us in triangle EOP, let us suppose this angle is theta is equal to theta. Let us suppose that this angle is theta, and this small angle and let angle COE is equal to the angle. This is angle D. From the geometry of this figure, we can calculate this distance EK. Now, by considering this angle EOK, in angle EOK, we can write the radius, that is radius EK. This radius EK is the radius of this slice. This EK is the radius of this slice, and it is equal to the r sin theta. This, if you use here the angle sin theta equals to the EK divided by hypotenuse, then we will get EK equals to r sin theta. Now, as this is the radius, therefore we can calculate the circumference of this small cell. Therefore, its circumference is 2 pi into r, and that r is this, that is r sin theta. This is the circumference of this slice CEF. Now, its width is this. This is the width of this slice, and we can calculate this width by considering this small angle COE this C is a R, and we can calculate here the formula theta equals to R upon radius. R upon radius. Here the arc is C and radius is R. Arc is C and radius is R, and therefore we can write for using this formula we can write the C equals to means this arc equals to R into D. This is the width, and that width is nothing but the width of this spherical cell. Now, by these two things, we can calculate the area of this cell, this slice. Therefore, area of spherical, area of this slice is nothing but a ring paper. Therefore, we can write here the area of ring or piece or slice equals to area equals to the circumference into the width. Circumference into the width. Circumference into the width. Therefore, we can write area of the ring or slice equal to circumference is this, that is 2 pi r sin theta into width is r sin theta. R d this with this equation we can calculate the area. Therefore, area of the ring or slice equals to 2 pi. These are and these are. It will be r square sin theta into d. This is the area of the slice. Now, we get here the area from now we can calculate the mass of this slice or ring, and after that we will differentiate. We will differentiate it for the potential. Therefore, mass equals to the mass of the slice. Mass of the slice equals to the mass of the slice equals to the area into density. This is the area, that is 2 pi r square sin theta d theta into rho. This equation gives us the mass of this slice. Now, then if EP equals to x, now this point P is at a distance x from this slice. If we cut this slice, number of like this slice, we can cut the number of slices, and the last slice here, its distance is approximately x equals to r. Therefore, we write here the if EP equals to x, then EP equals to x, then potential at point P due to due to small slice is given by dv equals to mass of slice upon minus mass of slice, given by minus mass of slice upon x into g. This is the potential at point R due to this slice is CEF. Now put the mass of this slice. Therefore dv equals to 2 pi r square sin theta d theta into rho upon x into g. Here dv equals to the minus 2 pi rho dx. Therefore now in triangle OEP, this triangle OEP, in this triangle, for calculating the value of the constants, we use the cosine law. The cosine law is like this: EP square equals to OE square plus OP square minus 2OE into OP cos of theta. But here EP is the x square, OE is we have calculated in OE, and OE is r square, as OE is the radius of this slice, radius of the spherical shape. R is the radius of the spherical shape, and this OP is the distance of a point P from the center of the spherical shape, minus 2 into OE is R, OP is small r into cos theta. OE equal to radius of this cell, and that is OE equals to R. Now differentiating our equation, we have, if we differentiate this equation, then what we get by differentiating above equation, we get this is 2x dx, x square, we get if we differentiate x square, we get 2x dx plus the differentiation of this constant term is 0. Similarly, this r is also constant, its differentiation is 0. This r is the radius and this is the distance, and both these are the constant quantities. Therefore, its differentiation is 0, minus 2r into r, and the differentiation of this cos theta is sin theta d theta, sin theta d theta, sin theta into d. This we can write. This we can write 2 dB equals to 2r into r sin theta into d theta upon only this. Okay, where r and r being constant, this r and this r is a constant. Now substituting this value in equation, this equation. Therefore, substituting this value in equation 1, we have suppose this is equation number 1, we have dv equals to minus 2 pi r square sin theta d theta into rho, which is the mass of the slice, upon into g upon r into r sin theta d theta into z dx into dx. Therefore, dv equals to, after simplifying, we get 2 pi minus 2 pi r rho upon r into z into dx. We are getting this way. Now, integrating this between the limits, x equals to ap, that is equals to r minus r and x equals to bp r plus r. This is the upper limit and lower limit for differentiation. Now I will write here therefore v equals to integration from r minus r and r plus r into 2 pi minus 2 pi r rho upon r into g into dx. Here in this we will take constant quantity outside the integration sign and integrate the remaining part. Therefore, here minus 2 pi r rho g into r, this total quantity is a constant quantity, and only dx we differentiate this, integrate with the dx term. If we integrate dx, then we get minus 2 pi r rho g upon r into x raised to its Its upper limit is r plus r and lower limit is r minus r. Now put the upper limit and lower limit minus 2 pi r rho g into r. Here r plus r plus r minus r. Now here this plus r and minus r will get cancelled and we get v equals to upper limit minus lower limit. Here this r and this r will get cancelled and the remaining part is like this, minus 2 pi r rho g upon r into 2r into 2r. Therefore this again I can write here this side and it will be, after simplifying, we get v equals to 2 pi minus 2 pi r rho upon r into g but 4 pi r square rho is equals to the mass of the cell. Therefore we can write v equals to these 2 and these 2 becomes 4. Here it is 4 pi r square rho. Therefore it is minus mg upon r, and this is the potential at point P due to this spherical cell. In this way, we have calculated the potential due to the spherical cell at point P, which is at a distance r from the center of the spherical cell.